The first chapter, electric charge and potential, we already completed with lots of numerical problem in the school. Today I start the second chapter, electric potential and capacitance. So first we discuss about electric potential. For the electric potential, initially we have to remember two things. Number one, electric potential exists at a point if the point lie on the electric field of any charge. Secondly, a positive charge body always moving from a point of higher potential to a point of lower potential. Now we have to know the concept of potential difference and potential. To know this, we consider a positive charge Q located at O. A and B are the 2 points on the electric field of the charge Q. Therefore, the point A and B having some electric potential. We want to determine the potential difference between the point A and B, for which we have to move a test charge from the point A and B. Okay, so here the test charge is indicated by Q naught. Now, when the test charge reach to the point B, due to the electric field of the charge Q, a force acting on the test charge, which is given here, F equal Q naught E, which is acting along the direction of electric field. To keep this charge in equilibrium, we have to apply an external force which having same magnitude of Q naught E, but the directions are opposite. So that's why this is the externally applied force, F equal minus Q naught E. So under this force, we consider the test charge moving a very small distance from P to Q. So therefore work done to transfer the test charge from P to Q is given by dW equal F vector dot dl vector, because this is the definition of work done, force dot displacement, equal minus Q naught E, as F is given here, minus Q naught E dot dl. So this is the expression for work done to move the test charge from point P to Q. Now total work done to move the test charge from A to B can be calculated as WAB equal minus Q naught integration A to B E dot dl. Okay, so therefore WAB by Q naught is equal minus A to B E vector dot dl, and according to the definition of electric potential, WAB by Q naught is known as the potential difference between the point A and B. That's why in place of this we can write VB minus VA equal minus of A to B E vector dot dl. Therefore we can say over the electric field between any two points, the potential difference can be calculated as the negative of line integral of the electric field between the two particular points. Okay, so next we know about the electric potential at a particular point. The electric potential at a particular point on the electric field of certain charge is defined as the amount of work done to bring a unit positive charge from infinity to that point against the electrostatic force due to the electric field. So mathematically electric potential is equal work done by charge. So now in this figure we want to determine the electric potential at point P. Therefore, we have to determine the amount of work done to bring a unit positive charge from infinity to the point B. So now from this equation of work done we can write W equal minus Q naught. We have to bring the charge from infinity to B. That's why the integration limit is infinity to B E vector dot dl, or V equal W by Q naught is equal minus infinity to B E dot dl. So this is the expression for electric potential at the particular point B. So therefore electric potential at any point can be defined as the line integral of electric field to bring a charge from infinity to that particular point. Remember one thing, electric potential is a scalar quantity and the SI unit is joule per coulomb, which is also known as volt. Okay. So now we have to know the potential due to a point charge. We consider a charge Q located at O. Due to that charge at a distance r at the point P, what is the potential you want to determine? For that we have to use the equation of electric potential. So therefore electric potential at P, V equal minus integration infinity to r, because here we have to bring the test charge from infinity to r, E dr. And from the previous chapter we know, from a charge Q at a distance r, the electric field E is given by Q by 4 pi epsilon naught r square. So that's why I put in place of E Q by 4 pi epsilon naught r square dr. Or V equal Q by 4 pi epsilon naught moves outside the integration, then infinity to r 1 by r square dr. By proper integration we get the final result as Q by 4 pi epsilon naught r. Therefore at a distance r from a charge Q, the electric potential given by Q by 4 pi epsilon naught r. This formula we have to remember, because sometimes we have to determine the electric potential at a point due to charge distribution. Okay, for example, see the diagram. Here P be a point, okay, and around this point there are n number of charges like Q1, Q2, Q3, Qn, like that. Okay, so we want to determine the total potential at the point P. So therefore what is the process? The process is, first we have to determine the potential at the point P due to individual charges. Okay, and as the electric potential is a scalar quantity, the total potential at the point P is the algebraic sum of the potential created by all the other charges. That's why the potential at point P equal Q1 by 4 pi epsilon naught R1. This is the potential for charge Q1 plus Q2 by 4 pi epsilon naught R2 plus dot 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 plus Qn by 4 pi epsilon naught Rn. So these are the total potential acting on the point P. Now by summation process we can write this equation as V equal 1 by 4 pi epsilon naught common summation n from 1 to n Qn by Rn. So this is the formula by which we can determine the electric potential at a particular point due to charge distribution. Okay, now this point is applicable whenever the charge distributions are discrete, but if the charge distribution is continuous. As we know from the previous chapter, there are three types of charge distribution: linear charge distribution, surface charge distribution, and volume charge distribution. For that type of continuous charge distribution, the electric potential can be calculated by the formula V equal 1 by 4 pi epsilon naught integration dq by r. Okay, so now remember this portion. After this we start with the calculation of electric potential due to electric dipole. Thank you, student.